Hello. Today we will be discussing the usage of sinusoids to solve a math problem. In order to begin, let's set up this background scenario. A tire swing with mass 5 kilograms is attached to a tree branch 5 meters off the ground with a pulley in such a way that the swing may be raised and lowered. The question we're going to try to solve with said swing is this. What is the equation for the swing when the initial amplitude at t equals 0 is 4.5 meters off the ground, the rope starts at 2 meters long, and shortens consistently at a rate of 25 centimeters per second? Quick note, we will be solving this as a math problem, and therefore will only calculate the swing free from friction, air resistance, and other factors found in physics. Now, before we tackle that problem, let's take a step back for a moment and solve another problem based on the same tire swing. If the rope attached to the swing is 2.5 meters long, and the initial amplitude at t equals 0 is 3 meters off the ground, what equation will simulate the height of the swing y of the pendulum if the period is 2 seconds? If you already know what I'm getting at, that's great. If you skipped the time on screen, you can bypass this problem and move on to the harder one. If not, that's fine too. Since we know we have a starting value when t equals 0 that is at the top of the swing, it makes sense to use a cosine function, as this will give us a starting value. We know that the starting value is 3, but we can't just set the amplitude to 3, as then it will be going underground for half of the swing, which is not usually what tire swings tend to do. Therefore, we will calculate the amplitude by seeing that the length of the rope is 2.5 meters, meaning that the minimum value of the swing must be this 2.5 meter length of the rope subtracted from 5, because the rope falls from the height of the branch, which is 5 meters, up in the air. In this case, that means the swing stretches from 2.5 meters to 3. Now we can write our equation that y equals 0.25 cosine t plus 2.75. But wait, that equation has a period of 2 pi. And the original question said that the period of the swing was 2 seconds, meaning we must multiply t by pi in order to reach a period of 2 instead of 2 pi. Now that we understand how to make this basic graph, we need to ask ourselves, when the rope is shortened, what will happen to the swing's amplitude? Its period? What about when it is elongated? A shorter rope moving at the same speed should have a smaller period, as well as a smaller amplitude, as since the rope impacts the movement of the tire swing, it has less maneuverability the shorter the rope. The opposite is true for a longer rope. Now that we understand one way to write an equation for the tire swing, let's come back to where we were before, the shrinking rope. In order to solve this, we will start by adding in what we learned in the last problem, bringing us to a cosine bx plus c. First step, find a. In order to do this, we need to write a linear equation that simulates the limit on the amplitude of the swing. It's linear because the rope is being raised at a constant pace. We will be keeping this equation relative to itself and not its height from the ground. The tire will reach the tree in 10 seconds if it is being pulled upwards at 0.25 meters a second, when the rope maximum is 2.5 meters. Therefore, a in this equation will be minus 0.1 t plus 1. Next, we need to find the period. The period of a pendulum is directly tied to the length. The period of the pendulum is the square root of L divided by G, where L is the length of the rope and G is gravity, or in this case, the square root of the quantity 2.5 minus 0.25 t divided by 1. When putting this into the equation, we need to take the reciprocal of this. Therefore, we get the equation the quantity minus 0.1 t plus 1 times cosine of the square root of 1 divided by the quantity 2.5 minus 0.25 t times pi times t. This is the final result when that equation is graphed. I have added 2 lines to show that it decreases linearly to 0 at 10 seconds. In conclusion, as the tire swing approaches 10 seconds, aka reaching the branch, it swings back and forth faster and faster to the point of reaching infinity. Now, of course, this is realistically impossible, but once again, we are calculating this mathematically and without regard to physics. So I guess that's it. Sources and a text are linked down below in the description, as well as a worksheet with these problems on it if you want to challenge a friend and see what they come up with. Thanks for watching.